Next, we are going to talk about Bézout's identity, which is quite important and used in many proofs, although it might not seem very intuitive. And the expression is given here for integers a and b. There exists integers s and t such that the GCD of a and b equals a times s plus b times t. Now, this means the GCD of a and b can be written as, let's say, a linear combination of the numbers themselves, a and b. And when some people look at this, they think that as plus bt must be greater than a and b, which is not the case because s and t are allowed to be negative numbers, negative integers. Okay, therefore such a linear combination is going to give you a GCD. And let's see the proof of this. How is this possible? Consider this set consisting of the linear combinations of the numbers a and b, so in the form of ax plus by, where x and y are integers, not necessarily positive, but the combination itself, ax plus by, is assumed to be positive. Okay, so this is, well, not assumed, but chosen, because this is the set definition. So I'm choosing the linear combinations of a and b that are positive. Okay, now obviously this set is non-empty because a and b are positive integers, or even if they are negative integers, I can take their uh, absolute values. And therefore, if, for instance, if you select x equals 1 and y equals 0, you get a. If a is positive, this is in the set. If a is negative, you just select x is as negative 1 and y as 0, and you get the absolute value of a, which is clearly in this set. So the set is clearly not empty. And remember the well-ordering property. S is a non-empty set of positive integers. Therefore, it must have a minimum element. This is the well-ordering principle. Any non-empty set of positive integers, it must have a minimum element. Let's call this D and assume that this is equal to a times s plus b times t for some pair s and t. Okay, so this is the minimum value of um, uh, the, the linear combination, the positive linear combinations of a and b. Now, by the division theorem, there exists integers q and r. Of course, r, the remainder, should be in this range, such that a equals dq plus r. Okay, so this is essentially dividing a into d. Q is the quotient and R is the remainder. Now, since R equals A minus BQ from this relation, I can plug in, instead of D, this definition here, AS plus BT, and write this as A times 1 minus S times Q plus B times minus T times Q. And this here, the value R, is in this form, a times x plus b times y, because s, q, t, a, b, any number you see here are integers. Therefore, s times q is an integer, 1 minus s times q is also an integer, t is an integer, q is an integer, t times q minus t times q, they are all integers. So this is a linear combination of a and b, which means R is a linear combination of a and b. And we have assumed that it's a positive number, okay, or rather a non-negative number. Therefore, R must be, if it is a positive number, which means if it is not 0, it must be in this set S, or it's just 0. Therefore, we can just say that R is an element of the set S union with the element 0. Okay. Now, we know that R is less than D by definition of division, and D is the minimum element in S, and therefore R cannot be an element in S, right? Because if R is an element in S, meaning that it's not zero, then it has to be by definition smaller than D. But that leads to a contradiction because we have defined D as the minimum element. Therefore, R cannot be in the set S, which means R must be zero. Okay? Since R equals zero, this simply means because it's the remainder when A divided by D, this means D is a factor of A. Now, if you apply the same argument to B, when you divide D by B, if you write something like this in between the relationship between B and D, you will arrive at the same conclusion that D is also a factor of B, which means D is a common factor of A and B, right? D is a common divisor of A and B. Now, this proves that D is a common divisor, but it doesn't prove that it's the greatest one. So if we can also show that any common divisor of A and B is less than D, we will be able to show that D must be the GCD. Suppose some integer C is also a common divisor of A and B. This means there are integers U and V such that A equals C times U and B equals C times V by definition of divisibility. Okay? And then, since D equals A times S plus B times D, because, well, we have defined it to be as such, and if you replace A with C times U and B by C times V, you get C times U times S plus C times V times T, which can be written in this form. And clearly, U times S plus V times T is an integer, which means by definition, C is a divisor of D, which means C must be less than or equal to D. Therefore, D clearly is the greatest of all common divisors of A and B, and by definition, that means D equals the GCD of A and B. And this shows you that Bézout's identity stated here is correct. Now, as I said, this looks like a non-intuitive result, and it doesn't really show you what to do with it, but it's used quite extensively in a lot of results, as we will use later on. But let me point out to you that the integers S and T in this formulation are called Bézout coefficients, and they are not unique. So this expression, the GCD of A and B equals AS plus BT, is satisfied for not a unique pair of S and T, but in a general sense, an infinitely many pairs of S and T. And it's not that difficult to find these pairs S and T. They can be found through the extended Euclidean algorithm. And let me show you a simple example. For instance, the GCD of 12 and 42 is equal to 6. And 6 can be expressed as 12 times minus 3 plus 42 times 1. So minus 3 and plus 1 are Bézout coefficients here. But they are not unique because 6 is also equal to 12 times 4 plus 42 times minus 1. Or 12 times 11 plus 42 times minus 3. Okay, so you see you can have many Bézout pairs for any given AB pair. So what is this extended Euclidean algorithm? Let's go back. to the definition of Euclidean algorithm. Here we have just exchanged the pair AB with the pair BR, where R is the remainder when you divide A by B. And if you just keep track of the remainders, you can find the GCD. But if you also keep track of the quotients, you can find the Bézout coefficients. How so? If you have this result where, for instance, in this example, the GCD turns out to be 7, you can work backwards to obtain a Bézout pair, Bézout coefficient pair. So start from 7. Here, 7 is the remainder. So you write 7 as, let me put it here, as 91 minus 14 times 6. So this relationship. Okay, now here, you replace the remainder in this equation, which is 14, that appears here, with this relationship here. So you write this as 19 minus 287 minus 91 times 3 due to this times 6. And when you expand this, you get 91 minus 6 times 287 minus, well, this is 18 times 91. Sorry, this one is plus because you have a negative here. And therefore, when you collect all the terms together, you get 91 times 19 plus 287 times minus 6. So simple, a simple backward substitution gives you, let me put this in more recognizable. Okay, so 7 is the GCD of 91 and 287, and these 19 and minus 6 is a pair of Bézout coefficients. So using extended Euclidean algorithm, which also keeps track of the quotients, you can simply compute a pair of Bézout coefficients for any given two integers.